Hello and welcome, class, to another general chemistry lecture, and here today we are continuing in Chapter 7, where so far we have discussed the molecular geometry of molecules, and we have also discussed potential intermolecular forces that occur between molecules. But before we really build off of intermolecular forces and those physical attractions, let's take a little bit of a brief respite and talk about how bonding occurs in the first place. So what we're going to introduce in the rest of Chapter 7 are two different bonding theories. The first, which we are going to be discussing today, is known as valence bond theory. This theory helps to describe the shapes of molecules, not just what they are, but rather how they are. Like, how do those shapes come to be? The second theory we are going to talk about, which is the next lecture part of Chapter 7, is known as molecular orbital theory. So we'll just put a pin in that discussion and focus on valence bond theory, as well as the hybridization of atomic orbitals for today. All right, so the premise of chemical bonding, which is the staple, the fundamental underpinnings of valence bond theory, can be seen below. The premise of bonding is that chemical bonds occur when atomic orbitals overlap. In other words, the electrons are going to be attracted by two different nucleic centers. So if we assume that there are two atoms coming together, let's say they're both hydrogens with an s orbital on the outside, as these two hydrogens with their one valence electron each, the electron being somewhere in and around this s orbital, as these two atoms come together, as the electron here begins to be attracted by this hydrogen's nucleus, and as this electron begins to be attracted by the other nucleus, they're going to come together, and we can see kind of smoosh into each other. This overlap of the s orbitals signifies that the electrons in each opposing atom are attracted by the other. So what this means is that there's going to be a chemical bond between the two different atoms because the electrons are holding the atoms together, right? This electron attracted by that atom, and this electron attracted by the first atom. However, there is an issue with this premise. Atomic orbitals, as they are naturally laid out, s orbitals, p orbitals, they do not allow for the molecular geometries that have been not only predicted by Vesper, but also experimentally observed. So we can conclude one of two things. Either the atomic orbitals themselves are incorrect, that we've been wrong this whole time, or that we're missing something. So a really good example of how it is that these atomic orbitals do not allow for the molecular geometries that we've been talking about, we can see by observing carbon down below, where its electron configuration here can be visualized using its atomic orbitals down below. So carbon has two electrons inside of its s orbital, as well as two electrons somewhere in its p orbitals. So our question is, how is it that four different hydrogens in the molecule of CH4 that we can see here on the right, how is it that these hydrogens end up forming 109.5 degree bond angles when the largest bond angle that we can even see is the bond angle separated from these two p orbitals inside of carbon with a 90 degree spread? Carbon's s orbital is perfectly spherical. It shouldn't matter where the hydrogens come in, and the p orbitals are kind of locked in place in this 90 degree spread. So how is it that a molecule like methane forms this tetrahedral combination or configuration? It doesn't make any sense. There's a big question mark here. All right, so valence bond theory then, while it was being developed between the initial premise in the 1920s and its final conception in the 1930s, addressed this exact problem. It addressed the problem by acknowledging what we've been saying the whole time, or this whole time, about electrons. They are very dynamic. The electrons are going to move around wherever they need to be in order to stabilize the overall atom and stabilize the overall compound. So atomic orbitals, as a result, begin to hybridize together to create new orbitals as the electrons change their paths. These new orbitals are going to orient themselves in the geometries that are predicted by VSEPR theory because they are the most stable configuration for these new orbitals. So for example, if we take carbon's one single 2s orbital, as well as its 3 2p orbitals, and put them in a blender and mix them together. So here we have one orbital, there's 3 orbitals. What we end up with at the end are 1, 2, 3, 4 new orbitals that are all positioned at 109.5 degrees apart from each other. These new hybridized orbitals have some characteristics from the s orbital. They have some characteristics from the p orbitals, right? It's almost like we married these things together, and the new hybridized orbitals are like the little baby that comes out on the other side. But the new hybridized orbitals are in the correct geometry for hydrogens to come in and overlap with and give us that really nice 109.5 degree bond angle that we would expect. All right, so valence bond theory so far, in conclusion, right, as we've been discussing, assumes or states that chemical bonds occur due to the overlap of atomic orbitals, and says that these atomic orbitals are going to hybridize in order to minimize the instability, right, in order to increase the stability of the central atom as the surrounding atoms, like in this case hydrogen, come into bond. All right, so what we're going to be focusing on for the rest of the day are what are these types of hybridizations that can occur, and what are the subsequent geometries that are the most stable for each of these new hybridized cases. Even more than that, how can we predict it? Like, how do we know which atoms' orbitals are going to come together and what types of shapes they're going to make on the other side? The type of orbital hybridization that will occur can be determined by observing what we call the steric number around a given central atom. And as a reminder, we have already defined what a steric number is, but just as a brief reminder what the definition is a steric number is the total number of electron densities around whatever your central element is. So for example, returning to our CH4 example, this central carbon is surrounded by 1, 2, 3, 4 different bonds, and these 4 bonds are considered to be electron-dense groups. So the steric number of CH4 is also going to be equal to 4. Now, if we turn our attention to the table down below, we can see that each of these steric numbers that we've discussed from 4, we can see they're listed 4, 3, 2, and then 5 and 6. This is the order with which we're going to be introducing the hybridized orbitals. And a central atom with a steric number of 4 has a geometry, according to VSEPR theory, that is tetrahedral. And what it means about the hybridization of the orbitals is that the sp3 hybridization, this is the labeling system that we use, the sp3 hybridization is what the orientation, how the orbitals need to come together in order to even make the geometry that we would observe. Now, the reason why we call it sp3 hybridization, we can think of like literally just back to the example that we introduced, our CH4 example. The central carbon had 1 s orbital and 3 p orbitals that came together, that melded together, that hybridized together. And that's what this label means. There's 1 s and 3 p's that came together to make this new hybridized shape. So in the event that our central steric number is 4, and we would expect to see an electron domain or an electron pair geometry of tetrahedral in the molecule, that means that we must have sp3 hybridization to make that happen. Now, the rest of these orbital hybridizations, we're just going to break down. So steric number of 3, we've seen already, gives us a trigonal planar geometry. Steric number of 2 gives us a linear geometry. Steric number of 5 gives us the trigonal bipyramidal geometry. And a steric number of 6 gives us octahedral. This should all be review from earlier in the chapter. The new information we can see here, which is an explanation for how the central atomic orbitals come together to allow for the geometry in the first place. So a trigonal planar geometry is caused by an sp2 hybridization, which means we have 1s and 2p orbitals coming together. The sp hybridization is what causes the linear geometry, and this is a breakdown of 1s and 1p atomic orbital hybridizing together. The trigonal bipyramidal geometry, so this big expanded geometry, does require the use of d orbitals, which was also previously sort of introduced when working through Vesper theory. And at the time I told you not to worry about how the d orbitals got involved with the expansion of the octet. Here today, we're actually going to explicitly lay out how does the d orbital get involved? Like, how is it used as a back pocket to allow for the expansion of the octet? The hybridization that must occur in order to allow for this expanded geometry is the combination of 1s orbital, 3p orbitals, and 1d orbital. Just one of them. All right, last but not least, steric number of 6 giving us an octahedral geometry corresponds to a hybridization, ooh, this is a typo, of sp3d2. We need our 1s orbital, 3p orbitals, and in this case 2 d orbitals in order to allow for this more not only expanded octet, but also for the specific geometry of the octahedral case. All right, so let's actually though break down what each of these hybridizations look like, how they form, and what the corresponding electron configurations end up being around these central atoms as their orbitals begin to hybridize. First and foremost, we are going to be observing the sp3 hybridized orbitals. So these are the same ones that we just introduced with our CH4 example. These are the combination of, as just previously stated, 1s orbital and 3p orbitals from our central atom, and the combination is going to result in 4 degenerate hybridized sp3 orbitals. And also as a reminder, the word degenerate means of the same, that's a same, it looks like a sorry, of the same energy. I want to be really clear with my writing. So 4 degenerate orbitals of the exact same energy. Each of these orbitals is exactly identical. So we take our 1s orbital, illustrated in gray here, combine it with 3p orbitals, and these 4 new sp3 orbitals have some s character, which is why the lower lobes are illustrated in gray. This is the s character of the orbital. And they also have some p character to them, which is why the upper section is illustrated in teal. So this is the p character. And according to Vesper theory, these 4 orbitals are going to spread out in 3D space to allow for minimized repulsion and maximize the stability. This means that these 4 orbitals are going to rearrange themselves in a tetrahedral geometry always. This is what gives rise to the tetrahedral geometry in any molecule that has a steric number of 4. Now let's coin a new term. This new term, known as the sigma bond, was first coined as valence bond theory was starting to be developed, put together, getting off the ground. What a sigma bond is in reference to is what we kind of conventionally call a single bond. This is the chemical bond that results from direct overlap of atomic orbitals, which allows for the sharing of a single pair of electrons via the single bond definition. So let's see how all of these terms kind of work together. We're going to put together this last big cohesive picture. So we've introduced what sp3 hybridization is. We've introduced what the geometry is that it results in. So our last but not least is let's actually illustrate what the electron configuration of this new hybridized atomic orbital set is. So this electron configuration listed here is specifically for that of carbon. So our central carbon has a valence electron configuration of 2s2, 2p2. Well, as the atomic orbitals come together, as they hybridize together, the result is 1, 2, 3, 4 totally degenerate, right, of the same energy, sp3 orbitals. And not only that, but each of these 4 electrons are going to be evenly dispersed throughout these 4 degenerate orbitals. 1, 2, 3, 4. The reason these electrons are not spread out in the 2s and the 2p orbitals is specifically because the 2s orbital is of lower energy. It may not appear to be so, because we don't generally illustrate the 2s orbital as being lower than that of the 2p, but it is a lower energy. According to the Aufbau principle, it's going to get filled first. Well, if these orbitals hybridize together and suddenly they are all truly of the same energy, the 4 electrons inside of this hybridized orbital are going to spread out. Now, what this means is that in the orbitals surrounding this carbon, so we have one orbital here, one sp3 orbital here, one here, and one here, is that inside each of these orbital lobes, we're going to have one unpaired electron. As the one unpaired electron is hanging out in space, another atom with an unpaired electron, like that of this hydrogen, here's one of our hydrogen's 1s orbitals, is also going to have an electron in it, a single unpaired electron, and these two things are going to come together and create a bond. Now, the single bond definition is what I've boxed here on the right, 2 unpaired electrons coming together and being shared between 2 atomic centers. The sigma bond definition we can see in the illustration on the left. As these 2 atomic orbitals overlap, what this signifies in 3D space is specifically that the 2 unpaired electrons are being shared, that they are being attracted both between the carbon and the hydrogen, which kind of smooshes the atomic orbitals together. So a sigma bond being illustrated in the picture on the left via valence bond theory signifies that we have a single bond by conventional covalent bond thinking. All right, so we've been talking a lot about the sp3 hybridization. Let's turn our attention to the next set of hybridized orbitals, the sp2 hybridization. So this is what occurs when we have a combination of one s orbital and 2 p orbitals, and these result in 3 degenerate hybridized sp2 orbitals. So we're taking 1 orbital plus 2 orbitals gives 3 new degenerate orbitals. This does mean, since a central atom with p orbitals generally has 3 p orbitals, one of those p orbitals is not going to get used, which is what we can see in the illustration down below. Our 1s orbital, illustrated in gray, and the 3 p orbitals, 2 of which are teal and 1 of which is purple, we can see merge together in the sp2 case, giving us 3 new sp2 orbitals, which are a combination of the teal and the gray, just like before, illustrating S and P character inside of these orbitals. But we can also see that we have one unchanged p orbital. This is the one that is illustrated in purple. This one unchanged p orbital does remain as a leftover. It is still present around the central atom. It's not a part of the hybridization. It's just kind of there. The orientation of each of these 4 orbitals, though, the 3 sp2 and the 1 p, as they come together, we can see in the shape down below. We call this a trigonal planar geometry because the 3 sp2 orbitals are oriented in this trigonal plane. We can see that the one unchanged p orbital, though, exists above the plane and below the plane. It runs perfectly perpendicular to it. All right, so let's get a sense for how the sp2 hybridized orbitals get involved with bonding, since, again, we've just been looking at the sp3 case so far. Well, here, just like in the single bond, sigma bond parallel, we're going to be drawing a new one. Here, we are going to observe the connection between double bonds, the sharing, quote unquote, of two electron pairs between two different atomic centers, and that of the pi bond definition in valence bond theory. A pi bond is a chemical bond that results from an indirect overlap of atomic orbitals that are adjacent to the bonding axes. So a pi bond, as we will see in a moment, is the direct result of having an unhybridized p orbital. All right, so we're going to see how all of this kind of fleshes out by observing the valence bond theory picture, its description for the molecule C2H4. Now again, we have the electron configuration for carbon, our 2s2, 2p2. So let's say we're just going to pick out this carbon on the left. Well, the carbon on the left, as we can see in the molecule down below, has a steric number of 1, 2, 3. The steric number equaling 3 is what tells us that the hybridization of the carbon is going to be sp2, and we're also going to have this one leftover p orbital as a result. All right, as we have found though experimentally / theoretically, the energies of the sp2 and the p orbitals, though not exactly the same, are pretty close. So close, in fact, that the electrons that are present in the carbon's electron configuration do spread out, one in each orbital, just like how we saw in the sp3 case. So we can see that we have one unpaired electron in each of the sp2 orbitals, and we have one also unpaired electron in this valence p orbital. So around the carbon in the structure below, we have our 1, 2, 3 sp2 orbitals with one unpaired electron in each. So here's 1, 2, 3 unpaired electrons. The remaining electron exists in the p orbital that is unhybridized, this p orbital that exists one lobe above the carbon, one lobe below the carbon in 3D space. Here is where the last unpaired electron is. Well, at a long or short, at a distance, we have the other carbon that is right next door nearby. This other carbon, we can see, also has a steric number of 3 and therefore has the exact same hybridized electron configuration. So it will have its 1, 2, 3 sp2 orbitals with 1, 2, 3 unpaired electrons in each, 1, 2, 3 unpaired electrons in each. And we can see that I've drawn these as downspun electrons. So the unpaired electrons on the left are upspun, those on the right are downspun on these carbons. Now, directly in between the carbons, following inside of this bonding axis, we can see that there is overlap of orbitals where I am circling right here. This overlap is what we would label, using the definition that we've previously learned, this is a sigma bond. Because the orbitals are directly overlapping and then also directly in between the atoms, here we have a representation of a single pair of electrons existing between and shared between these two carbon centers. So this is a sigma bond. Where the pi bond comes into play is with this last p orbital, this last unpaired electron that exists above the carbon and below the carbon. And this one I will also illustrate as a downspun. Well, we don't have direct overlap between these two orbitals. However, due to the short distance between the two carbon centers, these two electrons do see each other, and they will end up kind of pairing together at a long distance. This we can see as an indirect overlap, right? They're not actually physically touching at this long distance, but we call it an overlap nonetheless because the two electrons pair together. So our first electron pair exists in the form of the sigma bond, again, right down here. And our second pair of electrons exists above and below the plane as the orbitals kind of indirectly link together. This is what we call the pi bond. And together, the combination of a sigma and a pi, right, one sigma and one pi, gives us 2 bonds, which is exactly equal to a double bond. So in other words, according to valence bond theory, a double bond that exists between 2 different atoms can be broken down into a combination of a sigma bond and a pi bond. The sigma bond is our direct overlap. The pi bond is the indirect overlap that is the result exactly of this unhybridized p orbital. All right, so what I want to do here is walk through another example. This example, however, is one that is a combination of not 2 atoms that are the same, but rather 2 atoms that are different. And of course, the hydrogens are off here. They're going to be overlapping as well, following our previous sigma bond definition. But what is of interest is what happens between the carbon and the oxygen. So we are going to use this Lewis structure illustrated below for CH2O and use it to determine the electron configuration, the hybridization, and the valence bond picture of what is occurring inside of this molecule. All right, we're gonna do this together since this is a new and fairly esoteric topic, so don't feel the need to pause. We are going to work through this one together. All right, so let's start, as we must do when observing valence bond theory in conjunction with Lewis structures. We're gonna start by observing what the steric number is around each of the atoms of interest. And again, we are going to focus primarily on the carbon and the oxygen. We are focusing on these because we can see that there are multiple bonds that are forming, namely this double bond. We have some lone pairs, so that's what we're doing here, is we want to see how valence bond theory takes into account this structure. Now the steric number around our central carbon, steric number, is equal to 3 since we have one single bond, another single bond, and a double bond. So that gives us a total of 3 different bonds. The oxygen has a steric number that is also equal to 3, but it is due to the combination of a double bond, one lone pair, and another lone pair. So we do have to take into account lone pairs when observing the steric number, not just for VSEPR theory, but also for valence bond theory. So we have to keep that in mind. All right, I'm just gonna erase those again because I want to be able to draw. Okay, so what we're gonna do first is write out the regular atomic, this should be a C, I realize it kind of turned into an O, the electron configurations for carbon and oxygen. So carbon's electron configuration is that we have seen already. We have our 2s orbital, our series of 2p orbitals with 2 electrons in the 2s, and 2p electrons. Oxygen is going to have the same exact valence shell with a 2s orbital and a series of 2p orbitals, and its valence electron count is 1, 2, 3, 4, 5, 6. Now, according to the steric numbers that we have observed here, what they tell us is that in order for the 2 atoms to come together and bond in this particular configuration, they are both going to need to form sp2 hybridization. So we're going to need 3 different sp2 orbitals in each case and 1 unhybridized p orbital. And that's going to be true for both the carbon and the oxygen, again, because they both have steric numbers equal to 3. And according to our previous table, a steric number of 3 means that we need sp2 hybridization. All right, so now we're going to take our electrons as were previously illustrated and spread them out in the new hybridized orbitals. So the sp2 and p orbitals, again, are very close in energy, so we're going to take carbon's 4 electrons and spread them out. And similarly with our oxygen, we're going to take all 1, 2, 3, 4, 5, 6 electrons and spread them out. So we start with our hybridized sp2. go all the way across to the P, and then loop back around to the sp2. So we can see in oxygen, there are 2 paired up electrons in the sp2 orbitals. All right, so now let's start filling in the picture. In order to do this, I'm going to erase these arrows here, so give me a second. So let's start with carbon. So our carbon has 1, 2, 3 sp2 orbitals in a trigonal planar configuration. This is what gives us the trigonal planar shape around the carbon. And we're gonna have 1, 2, 3 unpaired electrons in there. 1, 2, 3 unpaired electrons. And again, I'm sticking with upspun electrons illustrated on the carbon. The last unpaired electron is going to exist in the p orbital above and below, unpaired pointing in the up direction. Again, I've just selected upspun or a +1/2 electron arbitrarily for this, just for carbon. All right, the oxygen. We are going to see, again, 3 sp2 hybridized orbitals arranged in a trigonal planar configuration. So there's going to be 1 here, 1 here, and 1 here. And as we start placing the electrons inside of these lobes, here's something that's really interesting to note. These 2 paired electrons inside of the sp2 orbitals correspond to the lone pair, or the lone pairs that are already present on the Lewis structure for the oxygen. These 2 lone pairs are exactly these 2 electrons in the sp2 hybridized configuration. So we can make a prediction that the lone pairs are going to have 120-degree bond angles between them, as well as between each of them and the bond, the double bond on the other side. So they are all spread out. The last unpaired electron inside of this configuration, I'm going to add as a downspun electron right here, and we can see the introduction of a sigma bond between the carbon and the oxygen as these 2 orbitals begin to overlap, and the 2 electrons in the form of a pair, a bonding pair, a covalent bond, a single bond, come together. Last but not least, we have oxygen's unpaired, unhybridized p orbital, just like carbon's, which is going to exist above and below the oxygen in this structure. And there will be a single unpaired electron, and again, I'm going to illustrate this as a downspun electron so it can actually pair with the carbons at a long distance like so. So this long distance, this separate attraction, this coordinated pairing of the electrons is what gives us our pi bond. So in our structure, according to valence bond theory, we have a sigma bond, we have a pi bond. Each of these 2 bonds in combination accounts for the double bond that exists between the carbon and the oxygen. Not only that, but we've also seen an example for what happens to the lone pairs, or rather, how do we account for the lone pairs according to valence bond theory. In the electron configuration itself, when we see pairs of electrons like this in the sp2 hybridized orbitals, that is generally a signifier that there is a lone pair somewhere on that atom in the Lewis structure. Okay, before moving forward, if you have any questions or concerns, or the clarity of my own hand-drawn illustrations are not quite up to snuff, I would strongly recommend that either you check out your textbook. In Chapter 7, they have a great number of beautifully illustrated, color-coordinated figures for valence bonding pictures like I'm trying to draw here. If you are not in my class and you've stumbled across this lecture, Wikipedia is a great source for illustrations of valence bond diagrams, as well as, just a general Google search, not Wikipedia related. If you go to the images tab, there are some pretty awesome illustrations there as well. So use your resources. If my diagrams are not clear enough, hopefully they've given you at least a foundation to kind of bridge off and further study on your own. So far, we have introduced the sigma bond and the pi bond in conjunction with discussing sp3 hybridization and sp2 hybridization. However, there are 3 more hybridizations that we need to talk about, so let's get those illustrated and then we can call it a day. So after the sp3 and the sp2 comes the sp. The sp hybridization is a combination of one s orbital and one p orbital. Now this 1 plus 1 is going to give us 2 degenerate hybridized sp orbitals. These 2 degenerate sp orbitals are going to be oriented in a linear configuration, which is what we can see in this diagram down below. So we're taking our gray 1s orbital and one of our teal p orbitals and mixing these things together. That is what directly gives us the 2 hybridized sp orbitals that again have some s character and some p character. We can also see though that the 2 purple p orbitals have now been left unchanged. They are unhybridized and they are just going to exist perpendicular to the sp orbitals in the structure down below. So as we allow for a stable geometry to kind of reconfigure and exist between these 2 sp orbitals and the 2 unchanged p orbitals, we can see that the teal orbitals down below have created, again, this nice linear configuration where we have one orbital on the left and a second orbital on the right. Do not be confused. These 2 things are not connected like how a p orbital is. They are 2 separate orbitals. One of our unhybridized p orbitals runs up and down, and our second unhybridized p orbital runs back and forth. So each of these orbital lobes are separated by 90-degree bond angles, or 90-degree orbital angles. And just like how we observed a molecular example for when either sp3 or sp2 hybridizations occur in certain molecules, we're going to do the same thing with the sp. In addition, we can discuss how this remaining unhybridized p orbital, this additional unhybridized p orbital, gives rise to triple bonds. So we've seen how single bonds are created according to valence bond theory and double bonds. Let's talk about triple bonds as well. So a triple bond is the result from the combination of one sigma bond and not just one pi bond, but 2 pi bonds. So let's observe the molecule illustrated here. This is ethylene? It's C2H2. The bond between the 2 carbons we can see in our Lewis structure is illustrated as a triple bond. So this is a really good clue to us that as we start drawing the valence bond electron configuration and picture, that we should have 1 sigma bond and 2 pi bonds. So let's see where the sigma and the pi come from. Well, first we're going to have to take our electron configuration for carbon. Let's just pick out, again, the carbon on the left. And we're going to rearrange the electron configuration into the new hybridized case, where there's going to be 2 sp orbitals and 2 unhybridized p orbitals. And also, as we have seen before, since coincidentally the energy of these orbitals are not so different, is that the electrons are going to spread out across the sp and the p. So we're going to have 4 unpaired electrons in each of these orbitals. Well, if we're focusing on the carbon on the left, one of the sp orbitals is going to be between it and the carbon on the right, and the other sp orbital is going to be here on the left between it and the hydrogen. We're going to have 1 unpaired electron in each, so 1 electron on the left and 1 electron on the right. As we turn our attention to the unhybridized p orbitals, there will be 1 p orbital that runs up and down. We'll put 1 unpaired electron there, and there should be another p orbital that runs back and forth. So these are all running along the XYZ kind of coordinate axes in Cartesian space. So here's our last unpaired electron here. So we have 1, 2, 3, 4 unpaired electrons across the 1, 2 sp orbitals and the 1, 2 unhybridized p orbitals. Now, coincidentally enough, the carbon on the right is going to have the exact same hybridization. We can see that because it does have a steric number equal to 2, right? That's our huge clue that we're working with a hybridization of sp. So the carbon on the right is going to have the exact same hybridized electron configuration. It will have one sp hybridized orbital on the left with one unpaired electron inside of it. So now we can see directly in between here, this is where our sigma bond is going to be, directly between these carbons, resulting from the direct overlap of their hybridized sp orbitals. Carbon's also going to have a hybridized sp orbital on the right, also with an unpaired electron. And I realize that I haven't been illustrating this in the previous molecular examples, but just to be explicitly clear, this unpaired electron is pairing with hydrogen's 1s orbital. So this hydrogen also has an unpaired electron, and that unpaired electron with its up spin is going to create another sigma bond directly between the carbon and the hydrogen. So we have a sigma bond between the carbons, a sigma bond between the carbon and the hydrogen on the left, and similarly in an unillustrated form, we have a sigma bond between the carbon and the hydrogen on the left. So we have sigma bonds all across this molecule, directly in between each of the atomic centers that are present. Now, I need more space to further illustrate the example, or the carbon's hybridization and situation here on the right, so I'm going to erase a couple of these arrows real quick. All right, so despite the fact that I have erased those arrows marking where the sigma bonds are, please keep in mind that they are still sigma bonds. Just because I erased the arrows doesn't mean that's changed. We have, though, placed both of the carbon on the right's hybridized sp orbitals as well as its unpaired electrons. So let's focus on the unhybridized p orbitals, where one, again, is going to run directly up and down with an unpaired electron inside, and one is going to run back and forth with an unpaired electron inside. Now, the ones that are up and down, we've already seen how the orbitals will indirectly coordinate with each other. The electrons inside will pair together over a longer distance. This is what gives us a pi bond up above. And now we can also see, because of these unhybridized p orbitals that run back and forth with a single unpaired electron, these are also going to coordinate over long distance. And this is going to be where our second pi bond is. So the triple bond that exists between the two carbon centers is the result of a sigma bond that is directly in between the two carbon centers, one pi bond that is above and below because of the unhybridized p orbital, and another that is going to run side by side as the result of the unhybridized p orbital. 1 sigma plus 1 pi plus 1 pi means triple bond. So our valence bond theory is able to take into account, according to its orbital hybridization picture, how single bonds, double bonds, and triple bonds form. So this theory is in complete harmony with everything that we have talked about so far when it comes to Lewis structures and stable molecular bonding. All right, so let's have some fun. Let's discuss where the d orbitals actually get involved with these larger expanded octet geometries. Let's talk about the sp3d hybridization. This is a combination of one s orbital and 3 p orbitals, as well as one extra d orbital. And this will give us 5 degenerate hybridized sp3d orbitals. So the orientation of each of these equivalent degenerate sp3d orbitals we can see is down below, and they are clearly making a trigonal bipyramidal shape. Well, let's start by writing out the electron configurations for phosphorus as well as one of our fluorines. Just one will do, and that'll give us a really good picture for how everything is going to be coming together, how the electrons are going to pair. In this example, I'm just going to use the sp3d illustration down below to kind of give us an idea for how the orbitals are arranged, but full disclosure, we have gotten to the point now we're trying to illustrate the valence bond orbitals, these hybridized orbitals all coming together is going to be a really messy picture, and they've already honestly been a little overlapped and messy, so I'm not going to try and confuse anyone. We're just going to focus on the electron configurations. So our phosphorus has an electron, specifically a valence electron configuration, that is 3s2, 3p3, and just for funsies, because these do exist nearby in energetic space, even though they're empty, there are 1, 2, 3, 4, 5 3d orbitals. They're just all empty. Now fluorine has a valence electron configuration of 2s2, 2p5. So let's focus on our phosphorus. Since that is going to be the central atom inside of this Lewis structure, it is going to be the thing that will be predominantly hybridizing. We can visually see what's going to be happening just by observing the electron configurations. So phosphorus needs to have 5 unpaired electrons of equivalent energy in order to accommodate these 5 fluorines, each with their own single unpaired electron. So we can already predict that we're not going to be making any pi bonds, no like double or triple bonds. We just need 5 single sigma bonding orientations. Well, phosphorus can't really hybridize its s and p orbitals together without still keeping an electron pair. What we need to do is find a way to disperse the electron pair, to find a new place for this one paired electron to go. Right, because even if we made 4 hybridized sp3 orbitals, this paired electron would still be paired no matter where it would be. In other words, we need a 5th orbital. We need a 5th place to push the electron into so it won't overlap with any of our other electrons. This is where we need this one unfilled, this one empty d orbital. It is nearby in energetic space. Just because it's empty doesn't mean we can't use it. So we're going to bring this d orbital, just one of them, into the mix. This is going to then give us a combination of 1s, 3p, and 1d orbital. 1, 2, 3, 4, 5 degenerate equivalent sp3d orbitals. And each of the 5 electrons that phosphorus has in its valence shell will be able to spread out 1, 2, 3, 4, 5. We now have 5 equivalent unpaired electrons in phosphorus's hybridized valence shell in order to partner and pair with all of the fluorine's single unpaired electrons. Since we have 5 fluorines, we have 5 unpaired electrons here. And around our central phosphorus, we can see we have 5 unpaired electrons here. This means as each of our fluorines comes in nearby around the hybridized sp3d orbitals, their unpaired electrons will be able to overlap and create 5 equivalent in energy sigma bonds. All right, so this is how the sp3d hybridization works. We're just grabbing one of those empty d orbitals, pulling it out from high energy space, and hybridizing with it to create 5 equivalent energy levels where our unpaired electrons can be. Last but not least, we have the sp3d2 orbital hybridization. This is the result of combining 1 s orbital, 3 p orbitals, and 2 d orbitals. So we have 1 plus 3 plus 2 gives us a total of 6 degenerate hybridized sp3d2 orbitals. A really great example of a molecule that has this geometry is sulfur hexafluoride. The central sulfur will end up with 6 different sp3d2 orbitals hybridized in space like this, where we're going to have 1, 2, 3, 4, 5, 6 positions where we can form single bonds, or sigma bonds, according to valence bond theory. So we've already seen the electron configuration of our fluorine. Fluorine with a configuration of 2 electrons in the 2s shell, and 1, 2, 3, 4, 5 electrons in the 2p shell. This is what allows us to have one unpaired electron that can come in, can overlap with sulfur's hybridized orbitals, and create equivalent stable bonds. Let's check out sulfur's electron configuration and see why it is that 2 d orbitals are necessary here in order to form 6 degenerate, again, equivalent energy hybridized orbitals. To start, we have a 3s orbital that has 2 electrons inside. We have 3 different 3p orbitals with 1, 2, 3, 4 electrons inside. And just like before, we're planning ahead. We're going to lay out in space the 1, 2, 3, 4, 5 empty 3d orbitals that are nearby in energetic space. All right, so if we turn our attention to the sulfur, it would appear as though we only have, just to use some former language, a bonding capacity of 2. Since there are only 2 unpaired electrons here, no matter how we would hybridize the s and the p orbitals, we would always end up with 2 pairs and 2 unpaired electrons. Well, this is no good, since we want to be able to explain why it is that 6 fluorines can come around sulfur and make 6 equivalent degenerate bonds. Well, we've seen already, according to the more advanced approach for drawing Lewis structures, how we can do that via the Lewis structure method, but how valence bond theory explains this is by saying we have our s orbital, we have our 3p orbitals, and if we want to be able to spread out these paired electrons, we're going to need more space. So we are going to grab 2 of the 3d orbitals, which will allow our first electron to move over into its own apartment, our second electron to move over into its own apartment, and giving us 1, 2, 3, 4, 5, 6 equivalent in energy sp3d2 orbitals, where each electron has its own place. Each electron can spread out, giving us an equivalent unpaired spread in 6 different directions: up, down, left, right, back, and forth. Now this does mean, and I realize I didn't say this with the previous sp3d case, we do also have leftover empty d orbitals just kind of hanging out right next door. That's totally fine. We don't need to worry about any higher ordered bonds or how these d orbitals get involved. They're just empty, there's nothing inside of them. If need be, we might be able to push some extra electron density in them for future examples, but for right now, we just don't need to worry about them. There are just 3 leftovers. All right, but each of these 6 hybridized sp3d2 electrons can partner up with one of the fluorines' unpaired electrons, allowing for 6 fluorines to come in and bond with our central sulfur via 6 different sigma bonds. Okay. So in conclusion, with our discussion of valence bond theory, we have, just to start from where we are and work our way backwards, the sp3d2 hybridization, which allows for an octahedral shape and can be determined even before writing out these electron configurations, because the central atom will have a steric number equal to 6. We have the sp3d hybridization, which allows for the trigonal bipyramidal geometry around the central atom and can be predicted via a steric number around that central atom equal to 5. We have the sp hybridized case, which accounts for the linear geometry around a central atom and can be predicted due to a central steric number equal to 2. We have the sp2 hybridized case, which describes the trigonal planar geometry and can be predicted by a central steric number equal to 3. And last but not least, we have the sp3 hybridized orbitals, which give us a tetrahedral geometry and can be predicted by seeing a steric number of 4 around our central atom. So with all of that, what am I expecting of you guys? What am I expecting you to be able to recreate? Well, at the very least, I would expect you to be able to start by drawing a Lewis structure, use formal charge to determine what the most stable orientation of the electrons are going to be in the form of bonds, and then observe your steric number. Once you have your steric numbers, you can determine the hybridization of each of the elements in the molecule. I may ask for some type of electron configuration, I may ask for some kind of picture, but at the very least, and most commonly, this is the type of problem I would be asking of you. Can you identify the steric number? Can you identify the hybridization for an element inside of a molecule? So I would like you to try that now. Please pause the video, get an illustration for what xenon oxotetrafluoride looks like, use formal charge to determine the most stable orientation of the electrons, check out your steric numbers, and pick out your hybridizations. Welcome back. Let's start by drawing a Lewis structure. We're just going to start at the beginning. So the Lewis structure for xenon oxotetrafluoride is going to look like the structure below. We're going to have our central xenon. We're going to have a double bond to our oxygen up on top, single bonds to each of these 4 fluorines, and each of these fluorines will have 3 lone pairs around them. So I'm just going to fill in all of these dots. And last but not least, there will be 1 remaining lone pair on this xenon. So if you started by counting out the total valence number of electrons, you should have gotten a core structure with single bonds everywhere, but by pushing a lone pair from oxygen in between it and the xenon, we can see that we actually have formal charges across the board, all equal to 0. So this is going to be the most stable structure. If your structure does not agree with this, double check that you had the proper valence electron count in your pool, double check your formal charges. If there are any confusions, please do not hesitate to let me know. But now that we have the most stable structure drawn, let's identify the steric number around each of these individual atoms, and we can use the steric number to determine or predict what the hybridization of the atom is going to be. All right, so let's start with our oxygen up on top. This oxygen has a steric number of 1, 2, 3. There are 3 different bubbles of electron density, 3 different locations where lone pairs or bonds are. Since we have a steric number that is equal to 3, this means that we must have sp2 hybridization, as well as, kind of in parentheses, we have 1 leftover unhybridized p orbital that's present. All right, so here's our sp2 hybridization. The fluorines, we can see there are 1, 2, 3, 4 bubbles of electron density, meaning that each of the fluorines, because they all look identical, are going to have a steric number equal to 4. So yes, even though the fluorine is a terminal atom, just like the oxygen, because its electrons can be found in lone pairs, it's also going to be hybridized in order to minimize electron repulsion. And this steric number of 4 implies that we have sp3 hybridization around the central fluorine. All right, last but not least, and we're going to be making a generalization here, so if you're coming from a more advanced class, keep in mind this is general chemistry. Let's observe our xenon. There are 1, 2, 3, 4, 5, 6 locations of electron density around our xenon. This means that the xenon has a steric number of 6. This steric number of 6 means that we are going to have an octahedral shape and a hybridization at the most straightforward level of sp3d2. This is what is going to account for the octahedral shape. Bare minimum, what I'm expecting, again, from you guys is to identify steric numbers and use steric numbers to predict what the hybridization for each of these central elements is going to be. From the hybridization of the central element, you can pick out what the electron configuration for the element would be in this hybridized state. For example, if we observe fluorine with its sp3, 1, 2, 3, 4 hybridized orbitals. We can take the total valence electron count of 7 and just spread it out. 1, 2, 3, 4, 5, 6, 7. And so now from this valence orbital electron configuration, we can see where each of the lone pairs is around the central fluorine in this tetrahedral configuration, as well as we can see that we still have that one unpaired electron, which is what is going to allow for a covalent bond with xenon in the first place. All right, so even though I didn't explicitly ask in this problem for an electron configuration, we can still see how it connects to this type of problem, and that you don't necessarily need to make it more confusing than what it is. If you can identify the steric number, you can identify the hybridization. And if you can identify the hybridization, you can rewrite an electron configuration in a pretty straightforward way. All right, but that is it for valence bond theory at the general chemistry level. So we've introduced hybridization today, the notion that our electrons can take on new shapes and new geometries in order to minimize repulsive interactions. Here we have a couple of example problems pertaining to valence bond theory, just its basic definitions, and how atomic orbitals and molecules hybridize in order to come together and form stable structures that match what our Lewis structures look like. When we come back, we're going to round out Chapter 7 by discussing a second bonding theory, molecular orbital theory, which helps to fill in some of the gaps that still exist to this day in valence bond theory. But until then, if you have homework, do your homework, and until next time, class is dismissed.